Namaste to everyone. I welcome my YouTube channel. I would like to start the topics Tensor Analysis Lecture 1 today. Today we will discuss the preliminary part of Tensor Analysis, which will include the basic concepts related to the tensor analysis. Some key terms are very necessary, which will be discussed one by one. Our first concept is superscript and subscript. In a term A, I, J, the index I is called superscript and J is called subscript. Again, in another term A, Ji, the index J is called superscript and the index I is called subscript. That is, superscript is at upper position and subscript is at lower position. Number 2. Dummy suffix. If a suffix U, I, here I appears as a superscript and subscript. That is, if a suffix is repeated in a term, is called dummy suffix. Another example, AI, XI. Here, suffix I is repeated in this term, then the I is called dummy suffix. Our next idea is Einstein summation convention. Number 3. Einstein summation convention. An expression a1 x1 plus a2 x2 plus dot an xn is denoted by sigma ai xi I1 to n. This concept is our traditional concept, but Einstein summation convention says that there is no need of using summation if a suffix appears as a dummy suffix in a term. That is, we may write ai xi equal to I1 a1 x1, value of I is 2, a2 x2, and so on, an xn. Therefore, we conclude that the dummy suffix denotes the summation. If we write delta I, our next concept is Kronecker delta. the symbol delta I j is called Kronecker delta if this equal to 1 for I equal to j and 0 for I not equal to j. Next, we start an example with problem to prove delta I equal to n. Here I, the index, appears as a dummy suffix. So, according to Einstein summation convention, it represents the summation. Therefore, we may write delta I equal to delta 1 plus delta 2 dot delta nn. Here we get I equal to j, that is I equal to 1, j equal to 1. That means its value equal to 1. Similarly, this is 1 and this is 1. We get n numbers of 1, so this equal to n. Our next concept is n-dimensional space. 5 now. N-dimensional space. As we know that any point in two-dimensional plane is denoted by xy, where x is the x coordinate of the point P and y is the y coordinate of the point P. In tensor analysis, we may write xy equal to x1, x2, 1 and 2 as superscript. Similarly, in three-dimensional space, we may locate a point by ordered triplet x, y, z. In tensor analysis, we write x equal to x1, y equal to x2, and z equal to x3. So, the point P is denoted by the coordinates x1, x2, x3. Similarly, we may extend our tuples. We may take ordered n tuple. Ordered n tuple x1, x2, xn. this is the coordinate of the point in n-dimensional space. So we may extend from 2 dimension to 3 dimension to n dimension. So this point is a point in n-dimensional space. Our next concept is transformation of coordinates. For example, we get transformation from Cartesian to polar and polar to Cartesian as follows. Any point P is denoted by the ordered pair xy in Cartesian system of coordinates. Here x is the x coordinate of the point P and y is the y coordinate of the point P. The same point in polar system is represented by r theta. The relation between two system of coordinates is r square equal to x square plus y square, that is r equal to root over x square plus y square, that is r is the function of xy. Similarly, theta equal to tan inverse y by x. We may write theta is the function of xy. In a similar manner, we consider the n-dimensional space. Let in x coordinate system any point is represented by the ordered n-tuple x1, x2, xn. The same point in x bar system of coordinates is represented by x bar 1, x bar 2, x bar n. The relation between two system of coordinates is x bar 1 equal to x1, x2, xn. That is, x bar 1 is the function of x1, x2, xn. Similarly, x bar 2 is the function of x1, x2, xn. And in this way, we may write x bar n is the function of x1, x2, xn. In short, we may write x bar I is the function of x1, x2, xn, where I equal to 1, 2, n. Here, if xi is a single valued and also real valued continuous function, and the determinant, that is Jacobian, del x bar I by del xj not equal to 0, then we may find the coordinates of x system of coordinates in terms of x bar system of coordinates. that is x bar 1 x1 is the function of x bar 1 x bar 2 x bar n, x2 equal to x2 x bar 1 x bar 2 x bar n, and similar manner xn equal to xn is the function of x1 x2 xn. In short, we may write xi is the function of x bar 1 x bar 2 x bar n, where I equal to 1 2 3 and so on, n up to n. So we may verify this, that the Jacobian not equal to 0 and also the relation between Cartesian system of coordinates with polar system of coordinates as follows. As we know that r square equal to x square plus y square implies that 2r del r by del x equal to 2x implies that del r by del x equal to x by r. Similarly, del r by del y equal to y by r. Again, theta equal to tan inverse y by x. Del theta by del x equal to 1 by 1 plus y square by x square into minus y by x square. This is equal to minus y by x square plus y square. Again, del theta by del y equal to 1 by 1 plus y square by x square into 1 by x, that is x by x square plus y square. Now we examine the Jacobian. Between two systems of coordinates, Jacobian J equal to del r by del x, del r by del y, del r by del theta by del x, del theta by del y. This is equal to x by r, this is equal to y by r, and this is equal to minus y by x square plus y square, and this is x by x square plus y square, y square. We can write this as equal to x by r y by r minus y by r square x by r square. This is equal to x square by r cube plus y square by r cube equal to x square plus y square by r cube equal to r square by r cube equal to 1 by r, which is not equal to 0. So our Jacobian is not equal to 0. So we may relate the Cartesian system of coordinates with polar system of coordinates as follows: x equal to r cos theta, that is x is the function of r theta, and y equal to r sin theta, that is y is the function of r theta. So we have verified that if Jacobian not equal to 0 and the coordinates are continuous single value and also real value, then we may find one relation between one system of coordinates with other system of coordinates, and also conversely we may write this. This is the idea of transformation of coordinates. Our next idea is transformation by contravariance and contravariant vectors. Now we will discuss about the transformation by contravariance and contravariant vector. Let coordinates of a point P in X system of coordinates be x1, x2, xn. The another point Q, which is very near to point P, the coordinates of this point is denoted by x1 plus dx1, x2 plus dx2, xn plus dxn. In x bar system of coordinates, the coordinates of the point P is written as x bar 1, x bar 2, x bar n. The coordinates of the point Q in x bar system of coordinates be x bar 1 plus dx bar 1, x bar 2 plus dx bar 2, x bar n plus dx bar n. The relation between two systems of coordinates be x bar I is the function of x1, x2, xn. Now we may find a small element dx bar I, dx bar I equal to del x bar I by del x1 dx1 plus del x bar I by del x2 dx2 plus del x bar I by del xn dxn. Here we get that in each term we get suffix is repeated 1 1 2 2 n n. So we may write it as dummy suffix del x bar I by del x alpha dx alpha. This alpha is a dummy suffix, and if we expand this, we may get del x bar I by del x1 dx1 plus del x bar I by del x2 dx2 plus del x bar I by del x3 dx3 plus dot 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 del x bar I by del xn dxn. So if we have knowledge of a small increment dx alpha in x system of coordinates, we may find the small increment dx bar I in x bar system of coordinates. Here del x bar I and del x by del x alpha plays an important role to evaluate this. This type of transformation is known as transformation by contravariance. This transformation is a small increment in x system of coordinates to a small increment in x bar system of coordinates. This type of transformation is a transformation by contravariance. Now we take some quantities a1, a2, an in x system of coordinates, and corresponding terms in x bar system of coordinates be x a bar 1, a bar 2, a bar n. Similar to 1, if we get transformation a bar I equal to del x bar I by del x alpha a alpha, then the components a1, a2, an are called components of a contravariant vector, and a bar 1, a bar 2, a bar n are components of contravariant vector in x bar system of coordinates. Here we have used the term vector. Vector is a special case of tensor when rank is 1. Rank, that is determined by counting this partial number of partial derivatives. Here this partial derivatives is 1, so rank is 1. One rank tensor is called vector. Here the vector is contravariant vector, or in terms of tensor it may be said that it is a tensor, contravariant tensor of rank 1. Our next concept is transformation by covariance. Covariance and covariant vector. Covariant vector. Now we have a scalar valued function phi, which is the function of x1, x2, xn. Here x1, x2, xn be coordinates in x system of coordinates. We may find values del phi by del x1, del phi by del x2, del phi by del xn, and corresponding values in x bar system of coordinates be del phi by del x bar 1, del phi by del x bar 2, del phi by del x bar n. Since we know that xi is the function of x bar 1, x bar 2, x bar n. Now we relate these components and these components. We may find del phi by del x bar I equal to del phi by del x1 del x1 by del x bar I plus del phi by del x2 by del x bar I plus del phi by del xn by del x bar I. Here we get that 1 is a repeated suffix in the first term, 2 is a repeated suffix in the second term, and similarly in other terms. So this we may write as a dummy suffix del phi by del x alpha by del x bar I. We may also write this as del phi by del x bar I equal to del x alpha by del x bar I del phi by del x alpha. So if we have the knowledge of del phi by del x alpha, as phi is the direct function of x1, x2, xn, that is the function of x system of coordinates, then we may find the values of del phi by del x bar I. So this type of transformation is known as transformation by covariance. Now let A1, A2, An be n quantities in x system of coordinates. The corresponding is in x bar system of coordinates be x bar 1, a bar 2, a bar n. The relation between two system of coordinates be a bar I equal to del x alpha by del x bar I, a alpha, similar to this. In place of del phi by del x bar I, we have a bar I, and in place of del phi by del x alpha we have a alpha, and this partial derivative is the same. Then the components a1, a2, an are called components of a covariant vector in X system of coordinates, and a bar 1, a bar 2, a bar n are called components of a covariant vector in X bar system of coordinates. We may write this equation in matrix form. Here a bar I equal to del x1 by del x bar I a1 del x2, as alpha is the dummy suffix, so it denotes the summation x del x2 del x bar I a2 plus 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 del x n by del x bar I an. Putting I equal to 1 to n, we may get a bar 1 equal to del x1 by del x bar 1 a1 del x2 by del x bar 1 a2 del x n by del x bar 1 an. Putting I equal to 2, a bar 2 equal to del x 1 by del x bar 2 a1 del x 2 by del x bar 2 a2 plus del x n by del x bar 2 an, and so on. A bar n equal to del x1 by del x bar n a1 plus del x2 by del x bar n a2 plus dot 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 del x n by del x bar n an. We may write these equations in matrix form as follows: a1, a bar 1, a bar 2, a bar n equal to del x1 by del x bar 1 del x2 by del x bar 1 del x n by del x bar 1 del x1 by del x bar 2 del x2 by del x bar 2 del x n by del x bar 2 del x1 by del x bar n del x2 by del x bar n del x n by del x bar n a1 a2 an. Here, from these equations, we get this matrix equation. If you are satisfied with my video, then click on the like button and do subscribe my channel.